So welcome everyone. I'm Venkat Guruswamy and I serve as the director of the Simons Institute here at UC Berkeley. And it gives me great pleasure to welcome you all to the Simons Institute as well as this week's workshop on role of TCS in modern ML, which actually kicks off our summer activities after the spring programs ended. Probably Simons Institute doesn't need an introduction to this audience, but just a couple of remarks. It was established in 2012 with a very generous grant from the Simons Foundation. And as all of you know, it has fostered a lot of collaborative research in theoretical computer science and related areas by convening a lot of people for thematic semester programs, which is the main kind of convening happening here. And in addition to core aspects of TCS, which are naturally a big focus, the Institute's programs also work on connections to other areas of computer science, as well as science and engineering more broadly. And the Institute also tries to be very nimble and forward-looking in terms of what theory can do, and it reacts to significant advancements in the broader computing landscape, of course, quantum and AI being the obvious examples these days. And in addition to these long programs, the Institute also hosts a very small number of very carefully selected workshops on key topics. And this week, we have one such very exciting workshop on the role of TCS in modern machine learning, while also providing an occasion to celebrate the birthday of Avram Blum, who's one of the pioneers of the field, and who also was a co-chair of the Scientific Advisory Board of the Institute and has been a friend and well-wisher ever since the Institute's inception. So that's extra special workshop this week. And some acknowledgements before I give you some bookkeeping things, and I'll hand over to Santosh. So first, I will really like to thank the organizers for their work in putting together an outstanding program with an amazing lineup of speakers. I just looked at the program and I was like, oh my God, now I need to move my schedule around to go to talks. So it made my life more complex this week, but it's a good kind. So the organizers are the organizing committee is chaired by Santosh Vempala, and also has Nina Balkan, Anupam Gupta, Nika Hagtalab, Katrina Liget, and Ishai Mansoor. So thank you, everyone, and thanks to all for coming. And I also want to acknowledge our significant funding sources, which, without which events like this cannot happen. Obviously, the Simons Foundation and Simons Foundation International, but also our industry partners, notably Google, Jane Street, Bridgewater, and Apple. And and we always welcome more industry partners. So if any of you is interested, please come talk to me. Before I hand over to Santosh, some bookkeeping. Food is outside, as you know, before the first talk and during the breaks. Lunch, you're on your own, but as you know, it's Berkeley. There are many excellent choices nearby. If you do need to leave your stuff while at lunch, there are lockers on the other side. And please, no food and drinks in the auditorium. Otherwise, we cannot keep it clean. Obviously, water bottles are fine. And if you're active in social media, please consider live reporting or blogging from the workshop. The Simons has a huge presence, and a lot of people outside who cannot be here can benefit. Of course, the event is also live streamed, and all the videos will be posted. It takes a village to organize events, and I really want to thank our staff who work tirelessly to make events like this happen. And and without further ado, so I'll hand it over to Santosh. Thanks.
Thank you, Venkat, and apologies for the nice program. But, I'm thrilled to be here. I don't want to take up too much time from Tom. So the workshop themes seem timely. Some of us, or most of us, are concerned about the AI winter coming, and we have to be prepared. or maybe it's how to. But then it's perfect because Avram always knows how to turn it into something positive. So that's why the themes go together so well. I want to thank all the Simons staff and the Institute for making this happen. Carolyn, Francis, and Ashley have been fantastic in responding and getting us everything set up. My fellow organizers for putting together a great proposal and program. And let me now introduce Professor Mitchell, who is a renowned machine learning researcher and started the first machine learning department, at the machine learning department at CMU, which has always been very friendly to theoreticians. So I thought, who better than Tom to get us started on theory and modern machine learning.
Thank you. Well, thanks. It really is a delight to be here for a couple reasons. One is, where is Avram? There he is. One is a chance to wish happy birthday to my friend Avram, who once looked like this. And he does. I know, it's amazing. How can this be? So I met Avram in the 1990s when he came to CMU as a beginning assistant professor. And since we're both interested in machine learning in some way, we spent some time talking. And then when I really got to know him was when we team taught our course together. And I found the web page. It's still there, thank you, Google, in fall of 1994. Now, I just did some arithmetic. If he's 60 this year, that means he was 28 when we team taught this course. And we went on, it was a very significant event for me because at the time, I was beginning to write a textbook in machine learning. And teaching with Avram was a way to broaden my thinking, different perspectives on the field. And so much of what I learned from him about things like sample complexity and irrelevant features and multiplicative rules for weight tuning and so forth, eventually found its way into that textbook. So thank you and happy birthday, Avram. The second reason it's a delight to be here is I really do think that the topic of this workshop, what is the role of theory in modern machine learning, is really fundamental to what we're doing. And so I thought about how to organize this, and what occurred to me is the times are changing rapidly. And one indicator of that is that there's conventional wisdom in the field, which I took for granted 5 years ago, and which I no longer believe. So I'll show you what some of the conventional wisdom from 5 years ago that I no longer believe is, and the rest of the talk is presenting 3 examples, which I hope will convince you that you should at least question it too. Okay, 1. The main mechanism for achieving machine learning is tuning parameters. That's how we train neural networks. Obviously, I don't believe it anymore. Machine learning must rely on big data and sophisticated statistics. I don't believe it anymore. Computer knowledge representations must have well-defined semantics, unlike natural language. I don't believe it anymore. So let me go through 3 examples to try to explain why I feel this way. The first is, let's build a classifier learning program that uses large language models. Now, why would you want to do this? I want to do this because the bane of machine learning for decades has been that we don't have a good source for inductive bias, for principles for generalizing from the specific examples that we see. And people do. People, for example, when you learn to play chess and you lose your queen, you don't need 10,000 examples of losing your queen before you figure it out. What happens is you reason about it. Why did I lose my queen? Oh, it's because my sister was attacking my queen with her knight, and she was attacking my king at the same time. And then I have to move my king. She's going to be mine. Okay, I'm not going to let that happen again. I just generalized away from all the details of the chessboard with that explanation, that kind of reasoning. I didn't mention the 3 pawns that she hadn't moved yet and the 4 pawns that I hadn't moved yet, because they weren't relevant to the justification. we could never have computer programs that do this kind of reasoning-driven learning because we didn't have computer programs that could reason reliably over broad domains. Now we do. That's why we want to do this. Okay, so let me give you an example. This is based on some data from an online education site called CK12. And the classification problem here is we've given an X, we want to label it with a 0 or a 1. And the X is going to be a triple. It's a question, like the transfer of energy from a vibrating object in waves that travel through matter is called, fill in the blank. And here are 2 hints. And the label indicates which of the 2 hints helps the students the most. And we know the truth because the website let us measure downstream student outcomes. And so we actually measured the effectiveness of these hints in helping the students. Okay, so that's the classification task. Every X is going to be a triple like this. Okay, here's the learning algorithm. What we're going to do using LLMs is for each XY labeled example, we're going to give it to GPT-4 in this case and ask it to justify why y equals 1 is the correct label for this. And when we ask it to do that, here's the justification it comes up with. It says, the more helpful was hint 1, which provided a concrete example and explanation related to the concept being asked about in the question. And then it rephrases that as a general principle. Okay, so this is what I mean when I say we finally have computer programs that can do some form of reasoning on this kind of stuff. Okay, what's the learning algorithm? The learning algorithm is have the LLM generate a justification for every one of the labeled training examples. In this experiment, we had 125 examples, so we have 125 justifications. And then the final step of the algorithm is take those 125 justifications and distill them into a concise list of principles, which I'll call a rubric for labeling the data. So when we do that, here's the rubric that comes out. It has 7 principles from those 125 justifications. I won't read it all, but the first one says, for example, connection to practical applications. In subjects like physics or chemistry, where abstract concepts must be applied to real-world phenomena, prioritize explanations that directly connect these concepts to practical applications. This will aid comprehension and help students see the relevance. Okay, so this is what it comes out with. This is what gets learned from the training data. No numbers, no parameters. If there's a parameter, its value is on this slide. This is what gets learned. Now we can use this learned information and try to improve our classification. If we now go back to, in this case, the training data, and give this rubric to GPT-4, and then give it just the X part, not the Y, and have it make predictions, it does much better than it did before we trained. And similarly on a test set. So this does work. So it's an interesting thing to think about. What it's doing is using the capability of LLMs to understand English and reason about it to produce this. By the way, this can be used not only to label which of 2 hints is better, it can also be used to generate new hints. That's another feature of LLMs. They can reason in multiple ways, given some information. Okay, so what does this, I already explained the algorithm. What does this do to our way of thinking about what theory should do? So here's our standard pack learning framing of function approximation. Thank you, Les. And so we have a set of instances. We draw some according to some unknown distribution, and we seek a hypothesis that agrees with the truth as much as possible. But now what does it look like? Well, now there are a couple things that are different. One is now the target function is not really unknown, because in order to have the system create a justification, I had to tell it what f was. And I said something like, the problem here, the label 1 indicates that hint 1 is more useful for students than hint 0, and vice versa. So I had to describe in English what that function was. So it's, in a sense, now there's a natural language definition of the function available. There's a set of hypotheses, but what is that set? That is actually, each hypothesis is GPT-4 is the interpreter, plus a natural language description of what the function is. That is, we want to pick a hint that helps the students the most, plus this learned rubric that we saw in the previous slide, the learned list of principles. So every hypothesis is essentially the learned rubric plus stuff that allows the language model to interpret that, to assign labels. We also have this oracle, which is the language model. We're using it, we're giving it as input x, y pairs along with the natural language description of the function. Pick the hint that helps the students, and it's outputting a justification in natural language. So it's a different kind of framing. We still desire the same output, but this is kind of an interesting kind of problem to think about. We can ask sample complexity style questions. Clearly, they're related to the oracle. And there's been some interesting recent work on using oracles. But it also raises the question of how do we characterize, for example, the complexity of the hypothesis class? It's sort of the hypothesis class corresponds to every rubric you could ever write down. How do we theoretically capture the ambiguity in the description of the function? If I say, choose which hint will help students the most, what does that really mean? Help them answer this question, help them pass the test, help them in their future career. So even the natural language description is ambiguous. Okay, that's example 1. Example 2. Conventional wisdom is that function approximation problem to be well posed. We say there's a function from x to y, and here are some examples. But if I talk to somebody on the street and I ask them what do they want to predict, they give me the y, not the x. They say, I want to predict the stock market. They don't say, I want to predict the stock market from these 6 variables. Nobody ever says that. The real problem is, I want to predict y, you figure out the rest. Okay, that was always off the table. That's a problem. Even though I tried to get several PhD students to take it on as a thesis, nobody was crazy enough to do it, but now you can. So let's use LLMs to suggest useful features. So here's an example. Suppose I say to my Python program called suggest predictors for target, suppose I say predict, or give me target predictors for the target number of applications to CMU ML PhD program. That's literally the input to the program. Here's the output. This is literally the output of the program. It says, well, the predictor should include historical weekly application submission counts to CMU. It's assuming we're predicting this weekly. Days remaining until the deadline. use Google Trends search volume for terms like CMU PhD. Use page views on the CMU Machine Learning Department, graduate admissions discussions forums, machine learning AI conference deadlines and acceptance announcements. Why that? Oh, by the way, everything gets a rationale. The reason it thinks this is important is many machine learning PhD applicants time submissions around their paper acceptances to strengthen their CVs. So this could be a useful parameter for prediction. And of course, visa and immigration policy news. Okay, so that's an interesting example. Here's another. I asked it instead, give me predictors for the number of influenza hospital admissions in California in the future. And here's its literal response, except for the colors. I added the colors. So it says, well, look at weekly influenza hospital admissions, but look at also influenza-like outpatient visits rates. Look at vaccination coverage in California, weather conditions, search trends, school calendar. You know, what's interesting about this is I'm working with the person who has the top flu forecasting system in the US, who is Roni Rosenfeld. And we're using this system to try to see if we can improve its prediction by producing and experimenting with additional variables. Turns out they're not using school calendar. But when we did some preliminary experiments with it, this really does matter. And the reason is, as the rationale says, holiday gatherings drive transmission spikes, school closures suppress pediatric spread. So it has an effect. Okay, so what does this do to our framing of the problem? Well, it does a lot of damage. We no longer have a set of instances X, at least in the same sense, right? We don't have a set of instances X in the sense that we have a feature vector and we know what the features of X are. What we do have, we still have a notion of instances. We're going to make this prediction every week. And so in some sense, each week is an instance. It's just that it's an undescribed instance. And there's still some probability distribution over those weeks. It's just that we're not, the old notation I had here conflated the notion of an instance with the features that we're going to use to represent it. We need to disentangle those two things. Now we do have a target variable scoped by space and time. So predict flu rates in California each week. And we have an oracle, but it's a different kind of oracle now, or at least it's the same LLM, but we're asking it a different type of question. We're saying for target variable y described in natural language, what would be the predictors x described in natural language? Okay, so the point there is that now we can have computers take on the hard part of the learning problem. We can start exploring how can we get computers to figure out what to predict from. Okay, the third final example is what if instead of single function approximation, we take a more reinforcement learning style view and say, well, we have agents and we want them to learn. And what if the agents could write their own code using LLMs as subroutines? What if they could self-reflect on every single thing every computation they do? What if they could explicitly choose what to remember for the future as part of a learning thing? And what if they could generate new learning tasks? So I have a early stage research project which I immodestly call Predict Anything. But it's an agent designed so that you could give it in text, which you want to predict, and it should work on that problem for a long time. You can think of it as an agent where the sensors and effectors are similar to the ones in Claude code: file, read, write, execute, and web interface. The system itself is a package of Python code plus associated files that the system writes and uses as its memory, calls LLMs. It has a self-reflection mechanism, which is implemented as follows. Every single Python function, when it runs, generates a log file. And that log file can be given to Claude, and it can analyze the run while it's also looking at the code that produced the run. And it has several learning mechanisms, which include tuning parameters. I don't believe that's irrelevant. I just believe it won't be the dominant method in 5 years. Because I think what will happen is we're going to use LLMs as part of the substrate, and we're going to build learning agents on top of them in exactly the way we're talking about here. So let me show you very briefly what happens if I say to this agent, I want to predict US unemployment monthly. Then the first thing it does is generate a list of possible predictors analogous to what we saw in example 2. Things like look at initial jobless claims, look at equity market performance, look at Google search volume for unemployment-related terms, so forth. So it produces those. Second, it identifies web sources using a search engine and downloads the data from those, tries to download the data from those web sources. And then, equally difficult, merge those data sets from different web sources that might be at different periodicities and different notations, different units. But in this case, it found on the web that it could get from the Federal Reserve data site called FRED, many of these things. The Institute for Supply Management site has other things. Google Trends has other stuff. So it locates these, and then it writes code, calling an LLM to help it, writes code to interface with APIs on these sites, downloads the data, and trains a neural network to make the prediction. So here you can see its prediction for June unemployment, if you're an investor, is that employment will drop a little from 4.3, which it currently is, to 4.23. And it has some data about model accuracy that shows that this model actually is not that good that it trained. Okay, so that's the prediction cycle. Now, what about learning? Well, part of the learning happens when it finds that it needs to get data from this site, and it needs to write code to do that. So part of the learning is that it's generating a code base. Currently has several dozen Python functions that download code from different websites that it has written. And then it's in a long-term process of debugging, because they will work, but there will be exception cases where they don't work. It'll stumble upon them. It'll notice that and try to repair. That's part of the learning. But what drives the learning really is the self-reflection. So that trace I just showed you, those are the log files. We can give those very same log files to, in this case, Claude code, which we do, call it as a subroutine, and it says, and ask it to reflect on that run. How did it work? Were there any issues that should be logged and dealt with in the future? And basically it says, I've reviewed the log files, the Python module source, and its design doc. Here's my analysis, what I read, what I verified. The final verdict is that it passes, but there are 2 issues identified. One is that Google Trends returned an error message due to upstream rate limits from Google Trends. So that's an issue that gets logged and will be dealt with in the future, hopefully. And the model underperformed the naive baseline, which is predict tomorrow's number is the same as today's number. But the UI correctly reported this, so there was no problem. It's just a disappointment in terms of model performance. So these two issues are automatically pulled out of reflecting, self-reflecting on the run, and they become new learning tasks to work on when there's time. Part of that logging of things involves, I'm going to skip this because I want to have more time for discussion. But I was going to show you some of the details of how it stores this in files for memory, but just enough as to say it keeps track of observations, like there are no rate limits for standard API keys on the Federal Reserve data site. It has some strategies for ambiguous queries. Order the search by popularity so that you'll get at least the most popular results. And it has some questions it's posing, like what's the best strategy for handling data gaps, missing observations in the data set? So it's reflecting and producing these kinds of issues to deal with in the future. Okay, so I don't know if I convinced you to doubt conventional wisdom, but the point here is that machine learning is starting to look very different from what it looked like before, mostly because of the availability of language models and their ability to deal with natural language as a representation of information, despite the fact that it's an informal representation, and their ability to reason imperfectly about nearly anything. There's hardly a question you can think of that you won't get some response for. And so this opens up. We used to have, remember data science and data engineers? Those were the people who designed the machine learning system. Think of the new generation of machine learning systems as including the data engineer. That's what many of these issues, much of what we're seeing here. For theory, that means there are a number of opportunities, but at the heart of them are questions like how do we capture natural language representations and their informality and the kind of approximate reasoning that language models can do? How do we model learning agents that have pervasive self-reflection? When Avram and I taught our course in '94, we never even mentioned self-reflection as a machine learning thing. I think it will be a very major part of going forward of machine learning. And how do we model agents that generate their own learning subtasks? So I have more questions than I have answers, but with this audience, this is the best chance for answers I'm ever going to get. So I'll stop here.
For a couple of questions while the next speaker sets up.
So let me say, so teaching that class was formative for me as well. So I worked in learning theory for a while, but it was my first time talking with someone who actually had things they wanted machines to learn. So for me, it was just an abstract set of things, you know. So that was really, it was really interesting. Is this cheating? No, we actually want this thing. So it was fantastic. So actually, your talk brings up an interesting. Okay, one thing I got out of it is that there are like a number of paradigms that. For example, explanation-based learning that people have looked at that in the past, that maybe now is a time when we could, there are things we can come back to that maybe the time wasn't right at that time. We didn't maybe have the ability to do some of those things, but maybe there are existing formulations that makes sense to go back to with the new world we're in.
Yeah, I do agree with you, especially around in the 1980s and early 90s, there was a kind of wave of work on what people called explanation-based learning. And the example I gave earlier about learning the night fork from one example and by explaining it to yourself is the kind of thing that got worked on there. There was a flurry of activity, but it died out. Why did it die out? It died out because there the notion of explanation was isomorphic to the notion of proof. And so in chess and board games, you can make proofs because you know the rules of the game. In the world, it's harder to prove things and illogical formalism. So that work died out mostly because there was no available way of generating explanations for what we wanted. Now we have those, so I agree with your comment that maybe it's time to go back through a lot of the history and just keep asking this question. Now. We should do the same with conventional wisdom. Tom.
So I worked on an application about 20 years ago predicting grasshopper outbreaks. It followed exactly that paradigm, although I was doing it in my head. And there's a backward chaining process that happens. Like, if I only knew soil temperature at 6 inches below the surface, I could do a good job. Unfortunately, there are no data sources for that. So now I have a new prediction problem. Predict soil temperature 6 inches under the ground. And it turns out you can get data to supervised learning to try to do that, and then use that classifier to synthesize the features you want and so on. So I think we should try it. But this probably would just do
That's a good point. And one thing you're highlighting there is that if you have an agenda of possible learning tasks to work on next, data availability is a key heuristic for ordering that agenda.
So I have two sort of unrelated questions. The first, it seems that you're taking the large language model as a given and not as an output of what I would expect it to be, the output of the learning algorithm.
Yeah.
I would expect many of those things. Okay, so now it's speculative. In some sense, much of what you showed was more about what I would call like fine-tuning over the LLM. But maybe the vision looking forward, it would get those fine-tunings could get incorporated as part of the model.
Yeah. It's a good point. And it is still very important to understand how to train LLMs and how to constrain them in different ways.
Than you think.
So I'm not arguing. I agree with you on that. But like you see, we can build on them. So to me, the analogy is compilers. Before there were compilers, everybody programmed in, assembly code. And then there were compilers, and it was important to work on those compilers and make them better and better. But then all of a sudden, a whole new branch of computer science opened up, which is, oh, wow, we have compilers. What kind of languages should we build? What kind of tools can we, and I think we're at a similar stage in the development. We need to keep improving the training of LLMs, but simultaneously, we need to start looking at the next layer.
And the second question, how do you envision you didn't talk about evaluation at all, because it's more like at the eye of the beholder. Yeah, look, this looks better,
Yeah.
I think we do need better metrics than like the log loss of the probabilities of something that is used now.
Yeah, I think we can, the reason I chose prediction problems for the never-ending learning task is you can evaluate that. There are a lot of things you can try to do that are hard to evaluate, but I do agree. And one of the lessons, I think, from Frontier Lab, Google and OpenAI over the past year or two has been, if you can evaluate success, then you can train a system to excel at it. If you can't, you're wandering in the dark.
Yeah, so just very quick comment, actually, I think similarly to Ishai. So I think you are, what you should compare to is not park learning, but maybe semi-supervised learning, self-training, zero-shot learning, because you are making an implicit assumption using machine learning terms. Your inductive bias is that the explanation given by GPT-4, the one that you used, are good for the task, whether hint 1 is better than hint 2. And once this assumption is true, then sure, you can use it to then self-train, to distill whatever the hints I give, and to self-train.
Yeah.
So this reminds me a lot more like semi-supervised learning, like in code training, you make an additional implicit assumption, not only about the form of the target function, similarly more generally semi-supervised learning, zero-shot learning, and so on. So kind of, I think it's a more explanation of what Ishai said.
It's a pretty subtle issue because the point here is, aren't you making some assumption about the LLM
Making
actually?
an assumption is good, because if it's not good, the outcome
If
is going
it's
to be
good or
terrible.
not good. So let me tell you quickly an experiment I did. I was ornery one day, so I woke up and I lied to it. I just flipped every label. And I trained it on, I told it was learning what works best for students, but I actually trained it on what works worse for students. I flipped every label. It had no problem writing justifications for why the other hint was better. Kind of like people. And it had no problem producing a rubric, distilling that out. It's kind of a funny rubric. And if you give that learned rubric to it, sure enough, the performance decreases instead of improves. So there's this funny thing where the data is actually really important. It can generate many plausible explanations, but knowing ground truth, in this case, it's hint number 1, really focuses it in a way that's kind of subtle and I don't fully understand. So I agree that it needs to be.
The same thing would happen in self-training. The data is important. The
That's
relation
right,
between the assumption and
self-training.
the data is important. So I feel like it's very...
Yeah, so it is
self-training,
related to self-training.
Zero-shot learning, semi-supervised learning are the starting points for beginning theory here.
So
Yeah, good
let's
point.
take it up
Okay.
in the break again. Let's thank Tom. So our next speaker is Adam Kalai. I've learned over time not to try to predict what he's going to say or do. But over the last few years, he's been using his